Welcome everybody. Today we have Professor Arran Fernandez, who is a pure mathematician and associate professor at the Eastern Mediterranean University, specializing in fractional calculus. He completed his bachelor's, master's, and PhD at the University of Cambridge, where he began as a youngest student at the university, aged 15, came top of his year to be the youngest ever senior wrangler. Since completing his PhD in 2018, he has worked at the Eastern Mediterranean University, firstly as an assistant professor and then as an associate professor. He also spent a year working in Sultan Qaboos University, also as an associate professor. His research interests lie in connecting fractional calculus with other branches of mathematics, such as abstract algebra, analytic number theory, Clifford analysis. His research achievements in this direction include extending Minkowski operational calculus to fractional PDE, expressing the Riemann-Zeta function as fractional differ integral of an elementary function, and defining fractional d-bar derivatives in complex and hypercomplex settings. He is also listed as an editorial board member for several international mathematical journals, including Communications in Nonlinear Science and Numerical Simulation, and Fractional Calculus and Applied Seminar Series. We are very happy to have you, Arran. You may please begin the talk.
Thank you very much for the introduction. Thank you to everyone who is here online to listen to me. So I'm going to speak about the fractional residue theorem. It is a short title. It's a simple concept, the idea of combining residue theorem with fractional derivatives. This is joint work with Egor Zaytsev, who works at Rochester Independent College in the UK. Sorry that the date is wrong on the slides. I just realized this now, but it's too late to change. I gave a version of this talk before a few weeks ago, and that's the reason why. Anyway, so the idea of the talk, I put one slide at the beginning just to introduce. I guess everyone in this seminar series is already familiar with the idea of fractional calculus. We seek to define derivatives to non-integer orders, basically, and this concept leads to fractional versions of the theory of differential equations, variational principles, etc. Many branches of calculus and analysis can be fractionalized. Fractional complex analysis is a particular interest of mine. For example, fractional versions of the Cauchy-Riemann equations, the residue theorem, these basic results from a first course in complex analysis, can we fractionalize them? It turns out that fractional complex analysis is much less studied than fractional real analysis. A lot of the people who work in fractional calculus, they assume real variables. Therefore, there are many research opportunities in combining fractional calculus with complex analysis. This particular project has an interesting story behind it, which I will come to later on. So I start my talk with some definitions, basic concepts from both complex analysis and fractional calculus. Then some historical background, both from the 19th century and from more recently. And the main result is in section 3, the fractional residue theorem, but most of my slides are in section 4 because we needed a lot of calculations to figure out how this theorem can be applied and used to calculate real integrals. Then I will conclude the talk with some future ideas for research. So I guess everyone here is probably already at least somewhat familiar with complex analysis, but because it's an interdisciplinary seminar series, let me give a very brief introduction just to show what complex analysis is about. So real analysis studies functions of real variables, for example, a function from R into R, or maybe defined on an interval or some other subset of the real numbers. Complex analysis studies functions of complex variables. So one of the fundamental objects of study in this field is a function from some domain, which means an open connected subset of the complex plane into the complex plane. We say that such a function is holomorphic or analytic if it is complex differentiable at every point. So in a way, these two words, holomorphic and analytic, are just fancy ways to say differentiable. But it turns out that differentiability in the complex setting is a much stronger condition than in the real setting. And this is part of the beauty of the field. This essentially comes from the structure of complex multiplication, because C, the set of complex numbers, is not only a two-dimensional real vector space, It's also an algebra. We have the structure of multiplication, the structure of division, and that's why the definition of a derivative makes sense in the complex numbers in a way that it does not in, for example, just R2, a two-dimensional real vector space. So if you assume this condition of being complex differentiable everywhere, then you immediately get smoothness, Taylor series, locally uniformly convergent, unboundedness. So many results come directly from there. Whereas in real analysis, you can have a function that is differentiable once but not twice, or smooth but no Taylor series, and so on. In complex analysis, you just assume differentiability and you get essentially everything. One particularly important concept in complex analysis is analytic continuation. I include a brief explanation of this because it's so important, even though it doesn't really play a very big role in the work in this presentation. I will mention it in the context of fractional calculus, but it's just something that's often not taught even in complex analysis courses, but it's very important to know. From my point of view, there are two different ways that analytic continuation can be done or can be used. Analytic continuation of relations and analytic continuation of functions. So for relations, we have some identity, let's say f of z equals g of z. F and g are two complex functions. We assume this identity is true on the smaller domain, U is a subset of V, and if f and g are analytic on the bigger domain, then the identity must be true on the bigger domain as well. This is a very rare example in mathematics of getting something for free. Normally, if you want to prove a stronger version of a result, then you need more work than to prove the weaker version. This makes sense. But in complex analysis, if you have some identity you want to prove, and you know both sides of the identity are analytic functions, then even if you want to prove it on the whole complex plane, it's enough just to prove it, let's say, on the real line, real interval between 0 and 1, and that is a set from which you can extrapolate to the whole complex plane for free without doing any more work. So it's an amazing fact, analytic continuation. The other way it can be used is analytic continuation of functions. So here we have a function f, just one function, which is analytic on the smaller domain. U is a subset of V again. And the uniqueness of analytic continuation says that there is at most one function which extends f to the bigger domain in a way that is analytic. So, you know, these are not two separate results. They're closely related to each other. But the important thing here is that it gives a natural, unique way of extending functions in many situations. So you have a function defined on a smaller domain. It doesn't always work. Sometimes you have a function defined on a disk. There is a singularity. There is no way to extend it to a bigger disk. But if there is a way, then it's unique. And that means it is the natural way to extend. I will show how this is important in fractional calculus specifically. So here are the basic definitions of fractional calculus. Again, probably familiar to everyone who's listening. We have the Riemann-Liouville fractional integral, first formula, Riemann-Liouville fractional derivative, second formula. There are these conditions on alpha. So alpha is the fractional order, x is the independent variable, and c is the constant. It's like a constant of integration, but in the fractional setting, we need it for both integrals and derivatives, fractional derivatives. C is a fixed constant of integration, usually taken to be 0 or minus infinity in most contexts, most applications. So can we introduce complex variables into these formulae? Can we make a complex version of these expressions? Well, alpha is already complex. I've written here a real part of alpha. So alpha is a complex variable. That's easy. We can use exactly the same formulae. There is no necessity here for alpha to be real. Complex valued function is also easy. We can write f equals f1 plus if2, consider the real and imaginary parts separately, and that's easy to define by the same formula. But usually in most of the work on fractional calculus, the variable x and the variable or the constant c are assumed to be real and x greater than or equal to c. The reason why that assumption is normally imposed is that then x minus t, when t is between c and x, must be a positive real number. So you have a positive real number to a power, any power, it can be a fractional or complex power, and that's easy to define. As soon as x minus t is complex or even negative, if you have a negative number to a fractional power, we immediately run into some problems like branch cuts. Do we define the argument of a negative number to be pi or minus pi, and so on? We get complications. So for this reason, this is often just assumed to be a real formula. Here is where the analytic continuation comes in. So if you look at the Riemann-Liouville integral, this first expression, it is defined convergent on the right half plane in a complex variable alpha. So alpha has positive real part, it's only half of the complex plane. Is there an analytic continuation to the left half plane? Yes, there is, and it is exactly the Riemann-Liouville derivative. So because of uniqueness of analytic continuation that I mentioned earlier, that means from this point of view, at least thinking about complex analysis, the Riemann-Liouville derivative is the unique natural extension of the Riemann-Liouville integral. There are other formulae, like famously the Caputo derivative, but with the Caputo derivative, you will not have continuity with respect to the fractional order. The term differintegral, this is the convention. Integral to negative order is derivative to positive order. So we take I to something with negative real part, then that is D, something to positive real part, which is exactly covered by this definition. And N here is a natural number because you take the floor of this positive non-negative real number and add 1. So N is a natural number, this is a classical derivative, this is a fractional integral. This analytic continuation fact is something that's mentioned in the classical textbooks, and it's easy to prove with a little knowledge of complex analysis, but it's somehow underappreciated in the literature. Not many people talk about this nowadays. And I even had some problems with reviewers and editors telling me that this is not true, or you need to give a proof, you need to give a reference. And so at some point I wrote a little conference proceedings paper just to explain some of the facts about complex orders in fractional calculus. So now I have a reference point. If I have any more problems with people sort of disbelieving this fact, I can point them to there. Which is not to say it's new work of mine. It was known, of course, in the classical textbooks, but I explained in more detail, perhaps, some of these facts. So let's look again at the Riemann-Liouville integral formula. What happens if we try to use a complex variable? If we try to let x go into the complex plane? Immediately, we get two problems. The first one is the fractional power function. X minus t can now be a complex number. How do we define fractional power of a complex number? We have a branch point at t equals x, which is one end of the contour. Branch points are fixed, branch cuts are not. So we need to choose where our branch cut is going. How do we choose that? Where do we put the branch cut? That's a choice that has to be made, and that's an immediate question mark of how we're supposed to do that. The second problem is in the complex plane, if we're integrating from c to x, there's not only one way to do that. These are 2 points somewhere in the complex plane. Do we follow a straight line? Do we follow a circular arc? And if we fix a contour, how does that contour interact with the branch cut? Is it above? Is it below? Does it cross the branch cut? Does it go around the branch cut? We have to think about all these issues. These naturally arise as soon as you start considering fractional powers in complex analysis. The beautiful thing here is that we can solve both of these issues with one idea. And that idea is equation number 1, which is the complex variable formula for a fractional differintegral. Now, we have a branch cut, so z, now I started to call the independent variable z because we went into a complex plane. In the w plane, the plane of integration, this fractional power function must have a branch point at w equals z. It must have a branch cut. Where do we put the branch cut? This question that was asked here. Well, we have another number involved in this problem. We have this constant c, and that can give us a way to fix the direction of the branch cut. So we say that the branch cut starts from where it must start from, that's fixed, and it passes through the point c. So it's a fixed choice according to the constant of differintegration that we already have. H is a Hankel type contour. Second problem, second question here, how does the contour interact with the branch cut? It's not just a straight line. Actually, it's a sort of closed contour because it starts at C and ends at C, but it's closed going from one side of the branch cut to the other. So it's not a standard closed contour where you can use the residue theorem and so on. It's a Hankel type contour. These are used in some topics related to special functions and so on. we start at C, we go under the branch cut, round the branch point, and back along the branch cut on the other side, going back to C. So here's a few diagrams to show how this works in different situations according to where is C and where is Z in the complex plane. The direction could be anything. Right, so important facts about this equation 1. It's a natural generalization of Cauchy's differentiation formula. It is equivalent to the Riemann-Liouville definition. This is straightforward to prove by typical complex analysis techniques. You show that the small circle integral goes to 0. The two straight line integrals become some exponential function multiplier times real integrals. The exponential functions become a sine function. You use the reflection formula of the gamma function. It's like a standard calculation. And what we have now is one unified formula that works for all fractional orders. If you go back to Riemann-Liouville, we needed to have a fractional integral and a fractional derivative, two different formulae, which is, you know, it's okay. There is an analytic continuation fact, but this is mathematically less elegant than having just one formula that works for all values of alpha, which is this formula. So this result can be found in the standard textbook of Samko, Kelbes, Marichev, Theorem 22.1. I think section 22 is all about complex approach to fractional calculus. So this is not new work so far, right? This is just some standard things that are well known for many years, but it's the prelude to what's coming. The complex approach to fractional calculus is rarely used nowadays. As I mentioned, most people now are just assuming that the variables are real, they're doing real integrals and so on. But there is this long history. Some of the famous names, probably you will recognize Sonin, for example, Letnikov, Laurent. So I looked up this paper, and it's not the same Laurent that Laurent series are named after. It's another guy with the same surname. So Laurent wrote in French, Krug, I think, in German, Sonin, Letnikov, Nekrasov in Russian. And we've got this series of papers. And for more detail about this, there is a nice survey paper from 1977 written by Bertram Ross. I want to take a minute to mention Bertram Ross. He was one of the important figures in the history of fractional calculus. The first international conference devoted to fractional calculus was held in 1974, organized by him, by Ross and his university in New Haven, USA. Also 1974 was the year of the first textbook devoted to fractional calculus by Oldham and Spanier. Another one of the early fractional calculus textbooks was co-authored by Ross. That was Miller and Ross. And that was actually the book that I first learned fractional calculus from. I studied Miller and Ross from beginning to end, and also Oldham and Spanier. So known about this guy since I first started studying fractional calculus. Sadly, he passed away in 1993, but his impact is still being felt. Speaking of, you know, the history of fractional calculus, I want to mention also a couple of other important contributors specifically to the complex viewpoint on fractional calculus. One of them is Thomas Osler. His PhD thesis entitled Leibniz Rule, the Chain Rule, and Taylor's Theorem for Fractional Derivatives. And if you look at that title, you realize these are some of the very basic facts of calculus: the product rule, the chain rule, and Taylor's theories, extended to a fractional setting and in an original enough way to be worth a PhD and a whole series of papers. So this PhD in 1970, and when I was a PhD student, I was reading Osler's papers that I could find online, but I couldn't find a copy of his PhD thesis, which was cited in all of these papers. So I sent him an email. This was like 2015 or so. And he kindly replied to me. He sent me the PDF of his thesis. It's now available online. I think he uploaded it maybe later, but at that time, it was impossible to find online. And he also mentioned that he lost interest in fractional calculus in the 1970s. So after he did these huge contributions that received hundreds of well-deserved citations, he went off into other fields. And one of the important things about his work is that he always used the complex approach. If you look at these papers of his, you will see many pictures showing contours in the complex plane and always complex variables. And it makes it more difficult because you have to think about branch cuts and so on. But that was always his setting. And he also collaborated with some other people in Canada who are still working today, I think, on this complex approach to fractional calculus. Sadly passed away in 2023. The other person I would like to mention here is Jerry Kuiper. His MSc thesis was entitled Fractional Calculus and its Relationship to Riemann zeta function, which again, just from the title, this seems amazing, right? There is Riemann zeta function, which is one of these very difficult functions of mathematics. One of the millennium problems concerns studying this function. And he expressed the Riemann zeta function as a fractional differintegral of an elementary function. MSc, Ohio State University, 1975. And this was one of my sources when I was first studying fractional calculus. I had the classical textbooks, but I also got hold of his thesis, and I, again, studied that. And he always used the complex analysis approach. Always his independent variable was a complex number. He talked about this analytic continuation fact. I learned about it the first time from him, from his thesis. So both of these guys, in a way, have been very impactful on my own development as a fractional calculus researcher, and sort of influenced me to always use the complex approach. So I would like to dedicate my talk to their memory. Jerry Kuiper, after his MSc, he went to work for Stephen Wolfram on Mathematica. So if you are ever using Mathematica with special functions, anything related to special functions, there's a chance you might be using some code that he wrote. He died at a very young age in 1995, I believe a cycling accident, and there is an obituary of him written by Stephen Wolfram on the Wolfram website. So perhaps people are getting, have seen too much history by now. Let's try to move on and talk about some mathematics. So I want to draw an important distinction here. What I've talked about up till now is complexifying fractional calculus, which means we start with fractional calculus, the Riemann-Liouville integral, and so on, these things that are known in the fractional field, and we try to make them complex. So we introduce, for example, a complex variable, complex alpha, complex x, z, and so on. Now, that is one interesting avenue, but there is also the question of, can we fractionalize complex analysis, which is something different. So that means we start with the classical theory of complex analysis, and we try to make fractional versions. Are there fractional Cauchy-Riemann equations, fractional version of holomorphic analytic property, fractional Cauchy's theorem, fractional Laurent series, fractional residue theorem? So this is a very interesting question to investigate, I think, or a set of questions really, because there's this very classical, well-known field of complex analysis, and not much work has been done to fractionalize this, to create a fractional version of this theory. And it's been a sort of pet project of mine for several years. And two of my PhD students graduated working on this, this direction, this branch of research. So there is Shema Buzwina, graduated 2021. With her, we wrote a paper on fractionalizing d-bar derivatives, which are closely related to Cauchy-Riemann equations. That work has continued since then. Wala Yassin graduated 2025, and with her, I have several papers actually, but recently we've got this fractional polyanalyticity, which is still ongoing, by the way. We're still working on trying to understand what these fractionally polyanalytic functions are, but that's essentially a fractional version of the property of being an analytic function, which is already something interesting, right? And had not been done much up till that time. There is another approach to fractional d-bar derivatives, which was kind of developed in parallel, but that was already talked about in a previous seminar in this series by Wala Yassin, so I'm not going in that direction. Let me focus on reference 9 here, my paper with Egor Zaytsev about the fractional residue theorem. That's what this talk is about. Before I get into the maths, I want to explain how this paper started, like what's the story behind it, because it's a very unusual story. So Egor Zaytsev, he is not a professional mathematician, he's not an academic. He works as a school teacher. He has no university level mathematical qualifications, not even a bachelor's degree in mathematics. But he has something more valuable, which is interest and enthusiasm for mathematics. And he created this Maths Appreciation Society in his high school where he works. And he was self-studying complex analysis, I believe, for the purpose of showing it to his students, these kids who are interested in maths. And while looking into complex analysis, he created this concept of what he called a pseudo-residue, because there is a residue theorem, And you can use the residue theorem to solve many real integrals. This is standard fact, often involving powers. And then he started to think, what happens if we make these powers fractional? And he proposed a formula, without proving it, but a formula that makes sense naturally, and it always gave correct results. So he was doing these computations of real integrals, and his formula always gave the same result as what the integral actually is. So he's found something, but what to do with that? He didn't think that it was going to be new research. He thought that probably this is something already known to the professional mathematicians. There must be some theory behind it. So what did he do? Firstly, he asked his tutor, who helped him to make the idea more mathematically rigorous, but wasn't familiar with the theory of fractional calculus. Then he went to ask on Mathematics Stack Exchange, where some of the people there pointed him to the textbook of Samko Kilbes-Merichev, the well-known book on fractional calculus, which, of course, he didn't have enough mathematical background to study that book. But he contacted then Stefan Samko, the first author, never got any reply from him, but started to contact some of his former students, such as Humberto Rafeiro, who did his PhD under Samko's supervision. And Humberto happens to know me, recommended Egor to contact me. When he contacted me, I had a look at his work and I thought, this looks really interesting. And I could already see the connection with this theorem about the one I mentioned as theorem 22.1 in the textbook, like showing the complex contour formula for a fractional differintegral. And so we started this research collaboration. We wrote this paper together, submitted it to a strong journal. We got very positive feedback from the referee, and now it's published in the Bulletin of the London Mathematical Society. So nice ending to the story, and I think an unusual beginning, or an unusual story from beginning to end, of how this project and this paper came to be. Now let's start actually doing the mathematics and showing the main results. So here's the classical Cauchy differentiation formula. This is saying the nth derivative of a holomorphic function can be written as a complex contour integral. Okay, so this is one of the results you will see in an undergrad course on complex analysis. The fractional version of that, what would we expect? We change this nth derivative to a fractional order derivative. We change the n factorial to a gamma function, and the n+1th power we can immediately change to a fractional power. And this theorem indeed is true. So n here is a complex number, but not an integer. And we get essentially the same formula. We just have to fiddle a little bit with the contour. So instead of being just any simple closed contour containing z, we need to account for the branch cut. So there is a branch cut from C to Z, and we integrate around that, basically. So it depends on the point C. It's non-local, whereas classical derivatives are local. This is a known fact about fractional calculus. Fractional derivatives are non-local. This theorem here, again, is not new. It's essentially the same as the one I showed earlier, this theorem 22.1 from the textbook. Here's the classical residue theorem. Of course, can be written, stated in different ways. I'm stating it like this. I'm assuming that the isolated singularities are all poles inside the contour, so we don't have any essential singularities. And this is a formula for the contour integral. N is the winding number, so this is a weighted sum of the residues. And here is the formula for the residue at a pole of degree n. So it involves an nth derivative. Again, what would you expect as the fractional version of this? Again, we would integrate around the closed contour, our function, and we would have some sort of fractional residue or pseudo-residue. And the pseudo-residue can be defined by this formula. Instead of the factorial, you have a gamma function, here a fractional derivative, and a fractional power. It all seems very natural. And this is essentially the result that we have. This is the main result. This is the fractional residue theorem. I'm going to show on the next slide, there is a figure to help to make this make sense. But let me just run through it quickly. So gamma is a simple closed contour oriented anti-clockwise. So it's simple and anti-clockwise, which means the winding number should be always 1. I will explain why we needed to make that assumption, but it's, in a way, it's less general than this because we cannot have any sort of contour. We have a function f, holomorphic on and inside gamma, except for the poles and the branch points. We assume the branch points are of power function type. So for every singularity, there exists a number n, not necessarily a natural number, such that this thing is holomorphic. We assume the branch cuts are straight and do not intersect each other inside the contour. That's just an assumption. If they intersect each other, it could get crazy. And we have this formula. Equation 2 defines this pseudo-residue concept, but if you compare it with the equation on the previous slide, it's basically exactly the same. We have a fractional derivative instead of an ordinary derivative. Fractional derivatives, remember, they're non-local, they depend on a constant. So we've got this constant of integration or differintegration C0. What is C0? I think it's more clear from the picture. So from each singularity, we've got the Z1, for example, that's a branch point. We have a branch cut going out. We assume it's a straight line. And we follow this branch cut. Where does it first meet the contour gamma? That's our point C1. So if you look at the branch cut from Z2, it actually meets the contour 3 times, but we take the first time it meets the contour, that is our point C2. Okay? So these are the contours and branch cuts that we use. These red parts, gamma 1, gamma 2, gamma 3, we kind of use those to prove the theorem. I'm not showing the full proof here, but it's basically using this result for fractional derivatives in terms of contours and some standard kind of railway contour argument for cutting the singularities out of the contour integral. Okay, so this is the result. This is the illustration. Let me make some remarks. Pseudo-residues are non-local. So look at the formula, equation 2. The pseudo-residue is not only depending on what happens for z close to z0, because we also have this C0, and this could depend on the behavior of f all the way from C0 up to Z0, along the branch cut, basically. Now, that's a standard fact in fractional calculus, that fractional derivatives are non-local, but also from the complex analysis viewpoint, it makes sense because if you have an integer order singularity, like a pole, then that's an isolated singularity, and you can completely describe it by what happens just in the small neighborhood of this point. But if you have a fractional order power, then immediately you introduce a branch cut, and branch cut introduces some non-locality because the branch cut can go away, not just near the point. If n is a natural number, then of course there is no branch cut because we have a pole, essentially. This does not depend on C0 anymore because it will be an integer order derivative, and we recover the classical residue theorem. So we can get the residue theorem as a special case of the fractional residue theorem, which makes sense because you take the fractional order to be an integer and you recover the classical result. So now we want to solve some real integral problems using this fractional residue theorem. So here's the 4 problems that we're going to solve. The third one is trivial, actually. We already know what the answer should look like. But it will be interesting to verify using this fractional residue theorem that we do get the expected result. However, before we start to work on these, we need to consider some lemmas on fractional differintegrals of some simple functions with constant of differintegration minus infinity. You will see why minus infinity is needed, but for now I'm just going to spend some minutes talking about how we prove these, how we solve these problems. So we have a negative power of z, or z minus a, we have a logarithm function, and we have logarithm squared function. We're going to get some formulae for them under suitable conditions. And here is where I'm coming back to Jerry Kuiper, that I mentioned earlier, because in his thesis, these are some of the things that he studies, at least the first 2 of these. He has, so this is Kuiper's theorem 4, which gives exactly a fractional differintegral of a negative power of z with constant minus infinity. Now, this is great, but there's a problem here. You see, he uses analytic continuation. Everything was complex for him. Now, the problem is this minus 1 to the power of nu. So what is minus 1 to the power of nu? If I tell you nu equals 1/2, what is that? Square root of minus 1. Is it I? Is it minus I? This is the difficulty that arises when you start to do fractional powers of complex numbers. So I looked at this result, I looked at this proof, and I couldn't quite figure out if this should be e to the power I pi nu or e to the power minus I pi nu. So I started investigating it, and actually it can be either depending on the domain that we are in. So here is a more rigorous result without writing minus 1 to the power of nu. So if you want it as one unified formula, it's this thing. We've got a power of z minus a over a power of a minus z, which eliminates the need to write any power of minus 1, because we've just got these two things, and they are defined using principal branch of a complex power function. If you want to involve powers of minus 1, then it has to be written either like this or like that, according to whether z minus a is in the upper half plane or the lower half plane in the complex plane. Quick sketch of the proof. If real part of nu is negative, which means we are considering fractional integrals, not fractional derivatives, and this condition, real part of m plus nu is positive, this condition will be needed all the way to the end. If under those two conditions, then we basically use Kuiper's proof. We start from z minus a either just above or just below the negative real axis, and we use analytic continuation to extend to the whole upper half plane and the whole lower half plane. We cannot necessarily extend across the real axis because of branch cut problems, essentially. Second part of the proof is we can use z derivatives to extend to fractional derivatives as well as fractional integrals. So if we have this result for fractional if we have it for fractional integrals, we differentiate with respect to z, and we get a result for fractional derivatives, which looks the same. Then the third part of the proof, which was something that Kuiper did not do, because if you look at the assumptions, Kuiper assumed that real part of n is positive, and I realized that we don't actually need that. We only need the real part of m plus nu to be positive. So this m can be negative as long as it's not too far negative, depending on nu. So the third part of the proof is extending using this composition result, relating the nuth derivative with the nu minus kth derivative of the kth derivative of any function. So when we use that, then if our power in here, if our m is negative, then we relate that to the positive case by just doing some ordinary classical derivatives, and we use this result to somehow relate between them when c tends to minus infinity. I'm not showing all the details because I've only got 1 hour here, and I want to focus more on the fractional residue theorem usage. Log function, the second one of these three lemmas. Again, there is a result in the Kuiper thesis, corollary 1. This is the fractional differential of log z, deduced from lemma 4, which was, I think it should be maybe theorem 4 instead of lemma 4. It was his result on fractional power functions. The problem here again is we have this power of minus 1, so we need to make this a little more rigorous. Here is the result, but basically Kuiper's proof is used unchanged, so we just deduce this lemma from the previous lemma. Okay, so this is the fractional differential of the logarithm function with constant minus infinity. Here's the formula. Okay, third lemma or third challenge before we start to do real integrals is the log squared function. This turned out to be more difficult than the other two. It took me a lot of work to figure out how to get the result rigorously. My first guess was to use the fractional Leibniz rule. You've got log z times log z. So there is a fractional version of the product rule. You should be able to write this differential of log z squared as some infinite sum, but the problem is the infinite sum involves negative order differintegrals, fractional integrals basically, and fractional derivatives of log z, as we see in this lemma, we need the fractional order to be positive. So that idea failed right away. Now there is this trick of differentiation, composition of fractional differentiation operators, so we can express the nuth derivative of log z squared in terms of the nu minus 1th derivative of the first derivative. Let c tend to minus infinity, and we get this nice result. So instead of log z squared, it would be enough if we could fractionally differentiate log z over z, which we can say is log z times 1 over z. Can we use the fractional Leibniz rule there? Again, no. Because we can take negative order fractional derivatives of 1 over z, but not unboundedly negative. That was the first lemma. In this lemma, nu can be negative, but it cannot sort of go forever because we need real part of m plus nu to be positive. So again, we have a problem. So at this point, I started to just forget about the fractional Leibniz rule. Let's find some other method. Now, the non-fractional case can be found in quite a easy calculation. You know, just this is like a basic calculus problem. Take the nth derivative of log z over z, you do some calculations on paper, and you figure out it looks like this. So we get the nth harmonic sum here, 1 plus a half plus a third up to 1 over n. How do we take a fractional version of this? The harmonic sum, obviously, you cannot add from 1 up to 1 over n if n is not an integer. Thankfully, we've got Bertram Ross coming to the rescue. So I found this in a paper of him. Maybe he was not the first person to write this, but this is where I found it. The psi function, Euler digamma function, that's gamma dash over gamma of n plus 1 is exactly the nth harmonic sum minus the Euler-Mascheroni constant gamma. So we make a guess that if you change n here to be a fractional nu, n factorial becomes gamma function, fractional power there, and instead of this harmonic sum, let's try to take psi of nu plus 1 minus psi of 1, which is the Euler-Mascheroni constant gamma minus log z. So equation 3 is our guess at the answer. You'll notice there is no constant of integration in this formula, so I've just written it as if we can do an ordinary derivative to a fractional power. But what's our constant of integration? Is it c? Is it minus infinity? And how do we prove this? So far, this is only a guess. So luckily, when I saw this, I felt that this seems familiar. I recognized the difference of two psi functions. This is something that appears in a lot of fractional formulae in the textbook of Miller and Ross. We have, in particular, the formula for the Weyl fractional derivative of a power function times a log function. You put mu to be equal to minus 1, you get the Weyl fractional derivative of log z over z. And this is nice because this is almost what we want. We have psi 1 minus psi of nu plus 1. Here we want psi nu plus 1 minus psi 1. So they're very close, not exactly the same, but that's because we have a Weyl derivative. So how do we get from the Weyl derivative to the Riemann-Liouville derivative? Weyl is not so popular nowadays, but basically it is right-sided Riemann-Liouville with a constant infinity. So it's like integrating from z to infinity. And we want to integrate from minus infinity to z. So it's like the two parts of the real line, right? X to infinity, minus infinity to x, and there's some kind of duality. And this duality can be encoded by transmutation relations, which is another topic that I've worked in. So I had to combine a lot of different knowledge to be able to get this result. Here's the transmutation relations between Weyl going up to infinity and Riemann-Liouville from minus infinity. The Q operator is a reflection operator, g of z to g of minus z. And Weyl is the transmutation of Riemann-Liouville by this Q. So if we put capital G of z to be log z over z, then we know the lowercase g of z, that's the Weyl differential of log z over z, which we've got from here. We know this from the textbook. And what's on the bottom then will be log minus z over minus z, it's capital G of minus z, and what's on the right we get from g of z. So this now is a proved identity, and from there we just want to find the Riemann-Liouville differential of log z over z. Well, log minus z can be related to log z. We use our previous lemma about fractional differential of 1 over z, and we find this result with a fractional differential of log z over z, which gives, this is exactly what we expected. If you go back and compare with equation 3, it is the same thing, but now we've proved it rigorously. We know the constant is minus infinity, and we get this blue formula. This is the fractional differential of log z squared. Okay, so now we've done our fractional lemmas. We're ready to start looking at the real integrals. The first real integral problem is this one. 1 over z squared plus a squared to the power m. A and m are some constants, not necessarily integers. This is the contour integral we want to use. It's a semicircular contour, and we're going to let r, of course, tend to infinity. So we want to get an integral from minus infinity to infinity. So we start with a finite semicircle. We let r tend to infinity. The fractional residue theorem gives us this identity. The contour integral is 2 pi I times the pseudo-residue. The constant here of this pseudo-residue is quite nasty because it has to be where the horizontal branch cut meets this semicircle, which has this formula. However, when r tends to infinity, this just becomes minus infinity. So we go to the limit and we get our real integral that we want equals the limit of the contour integral, because it's easy to show that the curved part goes to 0 when r tends to infinity. So we get pseudo-residue with constant minus infinity. By definition, it's given by this fractional differintegral. And we simplify, and then we need to use our first lemma to say that this fractional differintegral of this negative power function, we have a formula for that, we know what it is, and then the rest is some calculation. I'm sparing you the boring details, but we need to use the duplication formula for the gamma function and some simplification, and we end up with this formula, which my co-author checked by calculation, like putting in some values of a and m and computing the real integral, and it is a correct result. Second real integral problem is this one, now integrating from 0 to infinity, and now we're going to introduce a branch cut. Well, we already have a branch cut, but now we introduce a second branch cut. We have a keyhole contour, which is excluding the branch cut from 0, but we still have the branch cut from minus t. We use the fractional residue theorem, fractional residue at minus t with constant equal to minus r. Now this capital R, of course, is going to infinity. We want the integral from 0 to infinity. And we have this exponential multiplier because there's a railway contour above and below the other branch cut. So we find pseudo-residue with constant minus infinity. And that ends up being a fractional differintegral of a power function, which again, we use our first lemma to get a formula for this. We do some simplification, some cancellation, and we get this elegant formula, beta function over t to the power k, which again is verified computationally. The third real integral problem, this is the one that's actually trivial, so we know what the answer is, but let's check that we really do get the expected answer. So we're not going to take the contour integral of this function. We're going to take a contour integral of a logarithm over the same denominator. So again, we have two different branch cuts, one starting from 0 and one starting from, sorry, that should be minus a, not minus t. And this is what we get from the fractional residue theorem. The fractional pseudo-residue at minus a should be this point with constant minus r. When r tends to infinity, we get pseudo-residue with constant minus infinity. The log parts cancel, again from the railway contour, 0 to infinity, infinity to 0, above and below the branch cut. The log parts cancel. We find the pseudo-residue with constant minus infinity. It comes out to be a fractional differintegral of the log z function. We have our second lemma from earlier to calculate the fractional differintegral of log z. We plug that into our formula, and we get exactly the known result, essentially, for this integral. So it works. The method gives the right result. Finally, the fourth real integral problem, we have a log z inside the real integral, which means that we're going to need fractional pseudo-residue of a function with log z squared. So again, we use our keyhole contour, log z squared. The two railway contour parts here, above and below the branch cut, will give a term with log z squared, another term with log z squared. They cancel, and we end up with a constant on the top and a log z on the top. Now, because of the I multiplier here, we can ignore the first of these integrals by taking simply the imaginary part. We're going to take the imaginary part of both sides, and we find the real integral that we're looking for in terms of the pseudo-residue of this function. When we calculate this pseudo-residue using the definition, we get a fractional differintegral of the log z squared function, and that is exactly our third lemma from earlier, fractional differintegral of log z squared. We have a formula for that. We plug it in, and we find a formula for the real integral of log z over z plus q to the power of p. So these are our four examples calculating real integrals. Conclusions, we have established this fractional residue theorem. The pseudo-residues are non-local, depend on branch cuts, not just single points, as fractional derivatives are always non-local. We have various real definite integrals that we have shown this theorem can actually be used to calculate them. We're not saying these are new results for those real integrals. Of course, they been done before by other methods, but it's interesting to see that this new complex theorem can be used to solve these problems. And all of our results have been verified computationally to be sure that they are correct. So many future ideas could come out of this. For example, Laurent series, which relate to the residue theorem. The residue theorem classically picks out the -1 coefficient in the Laurent series. Can we get a fractional version of that? What about branch points that are not of power function type? So if we stop assuming that the branch point has just a power function times a holomorphic function, is there a fractional version of Cauchy's argument principle, which is closely related to the residue theorem again? This was one suggested by the referee of our paper. There are many special functions that have Mellin bounds representations involving fractional powers. Can we study them using the fractional residue theorem? There's a whole lot of new directions that we can start to go in based on this research. Here are the references. I think I've already mentioned all of these on the slides. Number 9 is our recently published paper, 2026 Bulletin of the LMS. And that's the end of my talk. Thank you for your attention.
Thank you very much, Arran, for the very interesting talk. For questions, please raise your hand. I'll call out your name in the order that they appear on my screen. I do not see any raised hands, but if you still have a question, you can please unmute your mic and go ahead with your question. Yes, Lutricio has a question, please. You go ahead.
Yes, same.
Thank you, Arran, for the nice presentation. It was really inspiring. Thank you so much. So I think I'm going to ask a stupid question. Maybe I missed something. So in your work, okay, we have this complex version of the residue theorem, but you did mention the Cauchy's integral formula. Is it also new, or was it done before?
Let me go back to what I think you're asking about. So the fractional version of this Cauchy differentiation formula, this is not new because this is actually the same as yeah, it's the same thing as this. Essentially, they are just writing the same thing in different ways, and this is already mentioned in the classical textbook, Theorem 22.1 in the Samko-Kilbes-Marechev book.
Thank you. So I guess so in this case we have a fractional version of this Cauchy's inequality, UV theorem, something like that, based on this.
Fractional version of what did you say?
Of Cauchy's inequality, for example.
I'm trying to remember what Cauchy's inequality is. There are too many things named after Cauchy. I'm not sure which one you mean.
Yeah, from this, I mean, when we estimate the nth derivative by the maximum of f, something like that.
Ah, right, yes. So you mean from this to get the inequality. Yeah, so I guess we could do that for fractional derivatives as well, yes.
Mm-hmm. All. Thank you very much, Arran. It was really nice to see you and hear from you. Thanks.
Thank you very much, and thank you for the question as well.
Does anybody has any more questions? You can either raise your hand or you can unmute your mic and ask your question. Yes, Alexander.
Hello, everybody. I hope the sound is well. So again, thank you very much for the wonderful presentation, and the story is really fascinating. The story with your co-author. All right. So my question is about Laurent series that you mentioned that in the future you're going, maybe you or maybe some other mathematicians are going to trying to find a structure of the Laurent series for fractional case. And my question is, so how can we define the pseudo residue in the Laurent series, fractional Laurent series. So in usual way, we define it as a coefficient before z to the minus first power, right? So, but in this case, how can we, in which way we should watch? So maybe some ideas.
I don't know. I mean, that's why it has to be a new research project, because it's not obvious how this will work, but it feels like there could be something there to discover. Obviously, we cannot take it as just a term in a series, because the fractional order can be anywhere in the continuum, which cannot be expressed as a series. But maybe instead of a Laurent series, we might be able to have a Laurent integral, which would be very interesting itself if you can integrate with respect to the fractional order. But that's just a wild guess. I really have no idea because I have not actually worked on this yet.
Thank you very much. All right.
Thank you for the interesting question.
Oh, can I say something?
Yes,
Yes,
Professor
please.
Marichev.
Okay. I evaluated several integrals which you demonstrated using my programs in Mathematica, and I can send you results.
Yes, sure. Thank you.
And the other question is how this your approach with for residues connected with classical approach. I need to see more examples.
Well, these are the examples that we have. I mean, my co-author actually did the calculations for these examples to verify them in Mathematica with some particular numbers. How they are related to the classical approach? Well, if the exponents here, for example, m in the first one or k and l in the second one, if these exponents would be integers, then we could use the classical residue theorem because we would not have any branch points, any fractional powers. It would just be ordinary derivatives. So we have extended from the integer case into this fractional case where these numbers, these can be any positive real numbers, for example, this L and K.
Now I am realizing projects with description elementary functions. We have about 40 elementary functions in Mathematica with names. And for each of them, I apply in particular different operations like fractional, integral differentiation, and integral transforms and so on, and look how it works with existing version and future versions. It will be interesting if we make experiments with you, maybe how your approach for evaluation corresponding residues. I have this comment also, residues representation through functions, how it fit together with our results.
Yeah, this can be very interesting.
But you don't have Mathematica. This is the problem.
Yes. And I also don't have skill with using Mathematica, but maybe my co-author will know more than me, or we can have some other collaborators. I don't know. It will be an interesting thing to discuss.
I sent you a notebook about 70 pages with our overview for Chinese translation of book with some co-kilbas about fractional differentiation. This notebook was written together with Professor Elina Shishkina, but you can find more short version in PDF published in English, not only on China. Yeah.
That was the paper published in Fractional Calculus and Applied Analysis, right? About 2 years ago.
2 years ago.
Yeah.
Archive maybe. Archive. Yeah.
Yes, I've seen it.
Okay, it will be interesting to communicate with you more. and with Egor also. Maybe we can continue this somehow.
Thank you very much. Thank you for your interest.
Yeah. Okay.
Egor, do you have a question?
How long we can talk right now? I don't know.
Well, now we
As
are
long
in
as
the
you like.
recording, so maybe after the talk has finished and the recording has ended.
Egor, do you have a question?
I just wanted to follow up on what Professor Marchev sent. I've also calculated one contour integral using the fractional residue theorem. And there, I think it's quite, this is the one I sent to you. I think it's also quite nice visually to see how the value of the integral in the fractional case starts depending on the radius of the contour. So I looked at the circular contour, so no real integrals at this point, purely contour integrals with circular contours. And you can obviously, the radius of the contour doesn't matter for the integer case as long as the all singularities are inside the contour. But for the fractional case, I've used, I didn't use Mathematica, but I've used Wolfram to verify computationally several integrals, which is actually what we discussed with my students yesterday, but that's beyond the point. So if you want, Professor Marchev, I can send you those results. I'm not sure exactly if that's something you sort of hinted at in your statement, but I also have that if you're interested.
Okay, sent. I will look.
Okay, do we have any more questions? You can either raise your hand or you can unmute your mic and ask your question. I assume that there are no further questions. So at this point, we close this talk here. Thank you very much, Arran, for this nice talk. We will see you guys next week.
Thank you.
Thank you. So